Hey, hey. If you can hear me, let me know in the chat if everything sounds good. It's only three of three of you watching so far, so hoping at least one of you will let me know. Perfect. Okay. I don't know what was causing the internet connection earlier, but I was having trouble streaming, so. Alright, cool. And let's just make sure the video looks good too. So let's switch it over here. Alright. Hey, let me know if video looks good and if the audio still sounds good, since there's been issues with that in the past. So let me know and we'll get started. Perfect. All right. Let's get rolling then. Let's see here. All right. So I made this worksheet about an hour ago. It's posted to the website at the top in the announcements. So if you haven't downloaded it already, you can go to the announcements section of my website and then just download this. This is another checkpoint worksheet that I made, which is based on all the topics we've covered since the last live stream. So that's mainly chapter 8 and 9, which is all the energy stuff, conservation of energy, and momentum. Now, for this one, I actually more or less completed it a little more closer to what I want to. So on this, it'll cover a few individual topic questions. So each of these 4 questions are just, if you know the topic, it's just one topic, and then apply the idea from that topic. I have a second section, which is conceptual multiple choice. So they're relatively straightforward. It's just to make sure that you understand what's happening conceptually, so you piece together the correct concept or equation that belongs with what's happening and just, analyze it conceptually. It's not really meant to be calculated out. And then the last section, which I only made one problem for this, is more of a comprehensive problem. So it combines concepts across both chapters, in this case 8 and 9. So we'll take a look at all this. Let's see here. Let's zoom into this. All right. So let's start with the individual topic questions. So these 4 problems. First one. The 75 kilogram person starts at the bottom of a hiking trail, which is inclined at a 30-degree angle, and walks along the path for 200 meters. Calculate the change in gravitational potential energy of that person that's walking along that path. So we're going to first start out by sketching out a very basic picture, which is that they are just walking uphill along an incline. So we're going to draw a right triangle for this. So problem 1. So we have just this right triangle to represent the incline. And so we know a couple of things in this situation. So we know that they're going to start at this point down here. And they're going to end at this point up here. So they're going to go from, call it some point A to some point B. Now we know that this person has a mass of 75 kilograms. So I'll write their mass. 75 kilograms. We know the angle of the incline to the horizontal, theta, which is 30 degrees in this problem. And we also know that they walk the path for 200 meters. So the path is along the diagonal, so we know that that length along the hypotenuse is 200 meters. So we should write here. Let's call this distance d. And the value of d is 200 meters. Okay. So we need to calculate the change in the gravitational potential energy. So we can first take a look at if we can just calculate that directly by writing the change in gravitational potential energy, delta U G. equals the gravitational potential energy final minus the gravitational potential energy initial. This is the easiest route that you could take if you just know the information about the initial and the final. So now the gravitational potential energy itself is equal to mgy, or mgh. So it's purely based on the height in these problems. So what we need to do is we need to define where the y is equal to 0 in the problem first. So typically we're going to set that to the lowest point in the problem. So we're going to say that this level down here along the same height as point A, that's going to be our y equal to 0. So we set the y equal to 0 anywhere in the picture, but ideally at the lowest point is a good choice for most problems. We plug this into final and initial. So the change in gravitational potential energy is mgy final minus mgy initial. So since we set the y equal to 0 at the lowest point in this entire problem, which is going to coincide with point A, we're going to say that the y initial goes to 0. So that just leaves us with mgy final, and we can just plug in those values. So we have that it's 75 kilograms times 9.8 meters per second squared times y final, which is, now you have a height here, but we don't know the height exactly. We're going to call that height h. Now, we get the height h by knowing the distance diagonally and knowing this angle here is 30 degrees. So to relate h, d and theta together, so that's going to be opposite hypotenuse, that's going to be sine. So we're going to use the sine function to do that. So off to the side here, I'm going to write that the sine of theta equals h over d. So I'm going to solve for h, so it's just going to be d sine theta. So h equals d sine theta. Plug in the value for d and plug in the value for the angle, and for that you should get that it's 100 meters. So 200 times sine of 30 should give you 100. And that 100 is what we're going to use here, so 100 meters of height. So we calculate this, and it gives us, so 75 times 100 is 7,500 times 9.8. Because it's in the tens of thousands, I'm going to write in scientific notation. So I'm going to express it as 7.35 times 10 to the 4th joules. So we have kilogram meters per second, that's mass times acceleration, that gives us a force in newtons. Newtons times meters gives you work or energy in joules. So that's how you calculate the gravitational potential energy in this problem. So because you didn't have the height, you need to first get that height from the distance traveled, and then once you have that height, you can calculate that change in potential energy. So let me know if there are any questions on this, and we'll move on to the next one. Okay. Looks pretty good. All right. And thumbs up is always good if you get it and you just want to be like, cool, I got it. So for number 2, there is a popular roller coaster ride which immediately launches riders in a cart with the total mass given of 3,000 kilograms from rest very quickly up to a high rate of speed. We can model the roller coaster like a spring system, which has a spring constant of 300 newtons per meter. So we start the cart at rest here at the beginning of the problem, and we're going to model the launching system as a compressed spring, which in this case is initially compressed over a distance of 100 meters. So from where it starts to the bottom of this ramp in this picture here, that's the distance we're assuming the spring is compressed over in the problem. So the spring will become fully uncompressed after those 100 meters. We're going to calculate the maximum height that the riders will go if they are released from rest. So the cart will go along the track, go up the tower, and we're going to solve for this height h that they're going to go up the tower to their maximum height. So this one here is a conservation of energy problem because we have information in the beginning of the problem, for instance, pertaining to the spring. It being compressed will give it potential energy stored in the spring, and we're going to take that energy and we're going to use it to move up higher. So we're going to convert that to gravitational potential energy. So we can write for this. So here's the setup. So let's label this point A over here. And we just want to know something about point B over here. Now you could think of it as, okay, well, could I break this up into multiple parts? So you have like a first part, which it's horizontal only, it only deals with the spring. And then the second part would go from there up to that height. But it's completely unnecessary because in the conservation of energy, it only cares about what you have initially and what you have finally. So start at point A and at point B. It only cares about those 2 points, with one exception, which is the work done by non-conservative forces. So when we write the conservation of energy, we can write it out in the following expanded format. We can write that kinetic energy final plus potential energy final equals kinetic energy initial plus potential energy initial plus an extra term which accounts for the work done by any non-conservative forces. So this is the full conservation of energy equation. Non-conservative work is going to be anything as far as forces that do work that are not done by the gravitational force or the spring force. At this point in mechanics, these are the only 2 things that are considered conservative, and everything else in this class right now is considered non-conservative. So for instance, normal force, tension, friction especially, those things which are not spring or gravitational forces are considered non-conservative. And if those forces do work in a problem, then you have work non-conservative. So A is going to be my initial, so I can talk about the kinetic and potential energy initial, and point B is going to be my final. Same thing there. So I'm going to expand out each term into what they are respectively. So for instance, kinetic energy is 1/2 mv squared. This is the final in this case. Now, in general, when you're talking about potential energy, there's 2 kinds of potential energy: spring potential energy and gravitational potential energy. So when you account for this, the possibility that you can have both in a problem, you technically do need to write both, and then cross out if you don't have it. So what I'm going to do is I'm going to show that when I write the potential energy here, in this case the final, I'm going to write two terms added to each other. I'm going to write a gravitational potential energy, mgy final, plus a spring potential energy, if I have it. So it's plus 1/2 kx final squared. So this is my gravitational and my spring potential energy put into there. Now, I'm going to do the same thing for the opposite side of the equation. I'm going to do k initial, which is 1/2 mv initial squared, plus. Repeat the same thing for my potential energy because it can again break into two terms. So mg y initial plus 1/2 kx initial squared. Okay. The last thing that we have in here is the work non-conservatives, in which we need to first ask, is there any non-conservative forces? And then once we determine what the non-conservative forces are, we're going to then ask if they do work. So in this problem, there is only 3 forces we're going to encounter that, could possibly do work. And that would be, for instance, the weight pointing down. That's the gravitational force, mg. We have the normal force perpendicular to the surface, in this case up. And while that mass is along, this horizontal stretch of 100 meters in the problem, and it's, being pushed by the spring is compressed, which means that it wants to stretch out, which means the force provided by the spring points in the direction it wants to stretch out, which is to the right. So we're going to label that force Fs for spring force. So again, our non-conservative forces will be everything except the things that we can talk about as potential energies. So anything that's not gravitational and spring are considered non-conservative so far. So that means there's only one force which is considered non-conservative. It's the normal force. But now, despite having a non-conservative force, we're not going to have any work done by it because the force, normal, is perpendicular to the motion. So there's no work done by that force. Meaning that this work non-conservative term, despite being the normal force work, it's just equal to 0. It will just go away. So we don't need to consider any work non-conservative in this problem. Now, this is a lot to write out. In general, you probably don't want to write all of this. This is what you should realize each term really is. So if you look at each of them, for instance, the kinetic energies, they're based on movement. If it's not moving, there's no kinetic energy. So you don't even need to really write the term if you know that it's not moving. Gravitational potential energy is based on height. If your height is 0, based on your coordinate system, you don't have it either. Spring potential energy is based on compression or elongation or stretch of the spring. So same deal there. The ones that stay and the ones that go. So what I'm going to do is I'm going to look at point A, my initial first, and I'm going to say, do I have any movement at all? So kinetic energy. In this case, it starts from rest. So I can cross out my kinetic energy initial because it's at rest. V equals to 0. Gravitational potential energy, well, rule of thumb is going to be that we're going to set the gravitational potential energy to be 0 at the lowest point used in the problem, which is at the level that it sits at initially. So at this level, where y equal to 0, we have no gravitational potential energy along that entire horizontal section. So I can cross out potential energy initial here, y equal to 0. And the remaining potential energy is a spring potential energy. So the spring is compressed. So that means the x value is not 0, so you will have a spring potential energy here. So that's the only term that's left initially. Finally, when it gets up to the top of that tower, when it reaches its absolute maximum height, the thing that we have to realize that's not directly stated is that upon reaching its maximum height, it implies it's the last moment before it rolls back down, which means that it has to have no velocity when it's at the top of that. So the V equals to 0 up there. So I can get rid of that initial kinetic energy. Which is interesting here because you notice that both the kinetic energy initial and the kinetic energy final both disappear in this problem. So when we solve this out, the kinetic energy is never involved in the problem at all, which is, it seems a little counterintuitive because you would think that you would use it at some point because it, despite it starting at rest and ending at rest, it does achieve a non-zero value of kinetic energy at some point during its path because it has to be moving. But again, this is not about what happens in the middle. This is about what happens initially and what happens finally. So in this case, it doesn't have kinetic energy at the beginning and it doesn't have kinetic energy at the end. So it's not even touched in this problem. So finishing the rest of this, we do have a height to end with, so we have a gravitational potential energy. And the spring will become fully uncompressed after it passes through the horizontal section. The spring is no longer involved in the problem. So the spring potential energy final goes to 0. So these will be all the reasons why we cross those terms out, and we'll have the following remaining terms. The remaining terms are mgy final, that's my gravitational potential energy at the end. That's it. And it's equal to 1/2 kx initial squared, so it's only spring potential energy to start with. So this statement right here just basically says that I start out completely with potential energy stored in that spring, and it uses all that potential energy stored in the spring to make it go higher up the tower, which is gravitational potential energy. So it's all converted into that at the end of the problem. We want the height in this case, so we're going to solve for y. So y final equals, we have this term which is 1/2 kx squared. I'm going to drop the 2 into the denominator. So I'm going to write kx initial squared divided by 2. And then we have mg in the bottom. So 2mg. We have all of the values for this, so we're just going to plug all of those in. So in this case we have 300 newtons per meter times x initial, which is the distance that it's compressed initially, which is 100 meters. So we use 100 meters. That is squared. Divide that by 2. Mass of the cart is 3,000. And g is 9.8 meters per second squared. Okay. So plug all those values in, and we'll get the value for y final, which in this problem we find it to be, so do the bottom, and then multiply across the top, 100 squared, and we get 51.0 meters. That is the final y value that we get, and with respect to our y equals 0 here, this is the height of the tower, so this is what we're defining to be the height h that it reaches. So again, applying conservation of energy, we have to understand all the different energies that we have in the system initially and finally. We cross out terms that are 0 for whatever reason, whether it's based on no movement, no spring compression or stretch, or no height. Those will be the conditions for particular energies being 0. And the only thing that we'll actually care about, which depends on the path that you take, so something between initial and final, is the work non-conservative term, but it's 0 in this problem, so we don't consider it at all. So you only care about initial and final. Boil it down to whatever energies you have to start with and to end with. Solve it and get what you want out of the problem. In this case, it's a 51 meter high cart or 51 meter high position that it arrives at of that tower for the cart. So Any questions on this problem? I think I'm gonna quickly fine-tune the camera real quick. I think it's a little bit bright, so I'm gonna do that, and I'm gonna just refocus it a little bit. Okay, that should be maybe a little bit better. Okay. So question. So the final spring potential energy is 0 because the spring is no longer stretched nor compressed. That is correct. I guess if you want to be really specific in the problem, you're going to assume the mass detaches from the spring after 100 meters. So we leave the spring in its uncompressed or unstretched position after it's moved through 100 meters. And the mass would just go up the tower on its own at that point. Let me know if that was good. No problem. So 3. A car with a mass of 1,000 kilograms is moving with an initial velocity of 35 meters per second when an impulse of 2.5 times 10 to the 4th kilogram meters per second as your unit is applied in the direction opposite to the motion for 5 seconds. What is the average amount of total force that was exerted on the car? So this deals with impulse. This is regarding momentum. So we're going to recall what momentum is and what impulse is and how they relate to each other. So for this one's a bit simpler. You'll find that the conservation of energy problems so far are the most, I guess, lengthy problems. They're not the most difficult necessarily. It really just depends on what your perspective is. But as far as length of problems, it's going to be conservation of energy problems. So now, for this one, the idea of an impulse is that an impulse is another way of saying change of momentum. So impulse is a change in momentum. Okay. So if we call the impulse I, which typically is I, on the occasion you'll find someplace using J for impulse. Nonetheless, whatever you want to call it, it's just equal to the change in momentum. So delta P. P is the momentum, and the momentum is defined as mass times velocity. So you can either go one of two routes. You can say that, okay, if I know that momentum by definition is mass times velocity, which tells me that the change in momentum is mass times the change in velocity, m delta v. Given that I know that, that's one route I could possibly take. But the thing is that we don't know entirely what the whole bit of information is regarding the change in momentum, because we have the mass, we have a velocity, but we only have a velocity. We don't know how the velocity is changing. In this case, we don't know, like, for instance, does the car come to rest? What is it doing later? We just know that the impulse is applied for 5 seconds, and we want the force out of that. So, now the question isn't asking for the change in momentum, it's asking you for force, which comes from relating this, using Newton's law, to the force, which is sum of forces external times the time interval. So if you needed to calculate a change in momentum, then you could either rely on using the relation to force, or you can use the definition of a change, which is final minus initial, and you can use the change in velocity. Now, in this case, because I do want to relate it to the force, I will use this. The other way that it would be written out, I guess more like Newton's law, is that the net force is equal to the change in momentum over change in time. So this is Newton's second law, just with momentum. So if we can figure out what the change in momentum is and the time interval, we can find that force. So now, in this problem, I tell you what the impulse delivered is. So if I tell you the impulse, that actually is just giving you the change in momentum. So in this problem, I directly hand you the impulse or the change in momentum. So the impulse just gets plugged into the top, which is 2.5 times 10 to the 4th kilogram meters per second. A lot of problems will ask you to find the change in momentum or the impulse. In this case, you're given what it is. And we know that this acts for 5 seconds. Combine the units, that'll be newtons for force, and you divide this. You should find that the net force is 5,000 newtons. And this would be the magnitude of your net force, assuming you're not throwing in the direction anywhere. So if you want to account for the direction, then for instance, the change in momentum or impulse would be negative. It's in the opposite direction of the motion, assuming that the direction of the motion is positive. And hence your net force would be negative 5,000 newtons to account for its direction opposite to the motion. So in this case, I only ask for the average amount of total force, so not really the direction. So we don't technically need to account for the direction. I just want the amount of force, so just the magnitude. But if you need the direction, just put the sign in for that. Okay. So this one was pretty straightforward as long as you know the concept of impulse and momentum. You can relate that to force and solve this problem pretty easily, just given you know what you're working with. Okay, let's take a look at this one. A firework is launched into the air, briefly comes to rest at the highest point in its path. At that moment, it explodes into 2 fragments with masses given, 0.40 kilograms and 2 kilograms. The smaller piece, in other words, the 0.40 kilogram piece, is found to be moving with a maximum speed of 50 meters per second almost immediately after this explosion. What is the speed of the larger piece after the explosion? So to solve this problem, you either need to consult Katy Perry because it's a firework, or you need to use conservation of momentum to solve this. So we need to write out the conservation of momentum. This is an equal and opposite reaction kind of problem. So for every action, there's an equal and opposite reaction according to Newton's third law. And that's where we talk about conservation of momentum. So anytime you have direct interaction between 2 objects or physical contact, you can use the conservation of momentum. So in this case, the 2 masses that separate off in the explosion, it's basically due to a direct interaction, or I guess there was physical contact at the moment of the explosion. They propelled off of each other. So for this one, we should write that by the conservation of momentum, that if you expand it out in its fullest, So based on the idea that something is conserved, meaning whatever you had before is what you have after. Conserved means that it stays constant or does not change. So the total momentum in the system initially, which is the momentum of 1, m1, v1 initial, plus m2, v2 initial, the momentum of 2. Okay, so this is the total system's momentum initially. And to be conserved, we would have the same thing after, but for the final situation. So the total system's momentum after is m1 v1 final plus m2 v2 final. If you have more objects involved in the system, 3, 4 more objects, you just keep on adding more terms. Whatever you're going to do to make it so it's the total of the entire system, you just add more terms. In this problem, initially is before the explosion, just before, and final is just after the explosion. So that means initially, neither object has any movement at all. It briefly comes to rest at its highest point, and that's just before the explosion occurs. So they should both have no velocity to start with. In the final situation, which is just after the explosion, they will separate off and go their own ways with some velocity. So we have just the right side left. So left side is 0, right side just copy down. Okay. Let's define what 1 and 2 is. So it doesn't really matter which one's which as long as you're consistent. So we're going to say that the smaller piece is 1 and the larger piece is 2. So M2 is going to be 2 kilograms and M1 is going to be 0.40 kilograms. Okay. So we're going to designate 1 and 2 as the smaller and the larger piece, respectively. I'm going to solve for how fast the larger piece moves in this. So we know that the speed of 1, v1 final, is 50 meters per second. And the other piece moves with a velocity which is an unknown, but we're going to find that based on this principle. So now, we're going to solve for, that should be final, not initial. So the stuff that I wrote so far should be final. I'm going to solve for 2 in this case, so solve for v2 final. So move the term over to the other side, so minus m1 v1 final equals m2 v2 final. Divide off by the mass. I'll group the masses together, so therefore v2 final equals minus m1 divided by m2 times the final velocity of 1. I wrote it in this weird way because I want to emphasize here that the speed of, or the velocity of one of them is going to be directly based on the velocity of the other one, but also based on the ratio of the two masses. So depending on what that ratio is, if one is twice as big as the other, or if it's 10 times bigger, or if it's the same size, that is what determines what happens with the velocities. So I don't even technically need to give the exact masses. I just need to say which one is bigger by how much. So in this case, mass 1 is 0.40 kilograms, and then M2 is 2 kilograms. 2 kilograms is going to be, I think that is 5 times bigger. So if you just simply said that mass 2 is 5 times larger than mass 1, you could plug in a fifth and it will give you the same answer. It doesn't really matter. So we take that ratio of the two masses, multiply it by the velocity of the other one, which is 50 meters per second. We take 1/5 of that, and we find that the velocity of the larger piece is minus 10 meters per second. Now that's the velocity. The minus sign is going to simply indicate that if this is one-dimensional motion, so we're going to assume that they split along the same axis, like this. So there's an x-axis going right through the motion, or rather the motion of either one is only along the x-axis. If that's the case, then one will just be in the negative direction compared to the other. So in the end of this, since I only asked for what's the speed of the larger piece, we're just going to say it's 10. So the speed of M2 is 10 meters per second. And that's how fast it's going after. Let me know if you have any questions on applying conservation of momentum, and we'll do one more problem with single topics. Yeah. Okay. Yeah, I miswrote that earlier, so I fixed that. That's good. Any other questions on this one? Okay. Oh, that was the last one. Okay, so that was 4. So now let's take a look at a few conceptual ones. So there's only 4 of these. They're meant to be a little bit more quick. You just think of the concept and then you find which one is true or... So 5, 2 objects are thrown. Mass 1 has twice as much mass as mass 2 and thrown twice as fast. Which of the following statements are true? So each of these statements, if you look at them, all have to do with kinetic energy, and it's saying how much more or less kinetic energy there is. So like twice as much, 4 times more, 8 times less, or they both have the same, etc. So what we're going to do here is we're going to quickly just write out the relevant concept, which is in this case we're just figuring out what amount of kinetic energy it has. So this is a technique which you'll want to keep in your toolbox of different things that you could do to approach solving a concept or a problem. This is a very powerful and simple tool that you can use to get answers very quickly. So for instance, start with the concept, which is kinetic energy. Okay. Kinetic energy, we know, has one definition, which is that it's K equals 1/2 mv squared. Now, in this problem, I tell you 2 statements. I tell you first that M1 has twice as much mass as M2. So I write that M1 equals 2 times M2. So for instance, if M2 was 5 kilograms, then multiplying by 2 gives you 10 kilograms for mass 1. The other statement that we're going to write is that it's thrown twice as fast. So that means the velocity of v1 is 2 times the velocity of 2. So for a speed of, let's say, 10 meters per second for v2, v1 will be 20. Now, here's how you use this concept I'm about to apply to get the answer very quickly. given that we're going to ask what happens to 1 in comparison to 2, because these statements both say what's happening to 1 in comparison to 2. For instance, mass 1 is twice as much, and velocity 1 is also twice as much. The result we're going to get is going to be for 1 in comparison to 2. What we're going to do is we're only going to pay attention to these numbers out front here, this factor of 2 for each case. So what we do is we write what's called a proportionality, especially if you have to do things like the MCAT, or this is a skill even beyond the MCAT. This is something that gets you an answer very quickly, so it's good to know how to do this. A proportionality is only write factors that change. If it does not change, don't write it. So for instance, the kinetic energy is proportional to, you use this little fish symbol, K is proportional to, so the only things that do change are the mass and the velocity. We ignore the 1/2 because it stays the same no matter what. So it's proportional to m, but v is squared, so you keep this squared. The only thing you do here is you plug in by which factors you are changing the situation by. So for instance, doubling the mass means you plug in a 2. Doubling the velocity also means you plug in a 2, but you are squaring that. The squares and such still stay attached to the term. So with this, you get a factor of 8 out of this. Doubling the velocity of something actually quadruples the kinetic energy because it's squared. Or let's say if you tripled the velocity. Tripling the velocity would result in a kinetic energy which is 9 times greater. So there's a stronger dependence on the velocity than the mass. So in this case, to answer the question directly, let's see here. Mass 2 has 8 times less kinetic energy than mass 1. So this right here says that kinetic energy of 1 equals 8 times the kinetic energy of 2. So when you get the 8 out of here, it means 1 in comparison to 2, since that's what you've been doing the entire time. So this reads M1 has 8 times more than M2. But now if you look at the way that this is worded, it's actually M2 has 8 times less kinetic energy than M1. It means the exact same thing, it's just the opposite way around. So that's just a little extra skill you can put in your bag when you're doing problems. If you know that you're just simply, for instance, doubling something, you can analyze the effect that happens as a result by just plugging in the factor into the equation and then saying, oh, hey, doubling the velocity makes it 4 times bigger. You're done. So we're going to do one more of these, but for this spring setup. So 2 identical springs are stretched the same distance, but have different masses attached. Spring B has twice as much mass attached as spring A, and we want to find what's true. Now, they're all talking about potential energy here, and we know that the potential energy stored in a spring only depends on a couple of things. The first is the spring constant, which we're not changing in this problem, and x, which is the stretch or the compressional distance, but that's also not changing in this problem. So if neither the spring constant nor the stretch or compression of the spring is changing, it's completely identical here. You can see everything is the same except for the attached masses. The answer is that the potential energy is actually the same, because we're not changing anything that involves the potential energy here. The masses are not part of what gives it potential energy in that setup. So that's kind of an important thing to know conceptually. Number 7 is based off of the problem that we actually did. A firework is launched to its highest point in the air and then explodes into two pieces with different masses. After the explosion, which of the following are true? So you have to think about each of these statements here. They are a little bit different, but they are related. So the first statement says that the larger piece has a larger momentum. That's not true because it's an equal and opposite reaction in this case. According to Newton's third law, it's an equal and opposite reaction, so the force on one is the same as the force on two, just in the opposite direction. But because momentum is tied directly to force, you can say the same thing about the momentum. The momentum of one is equal and opposite to the momentum of two. So in other words, one piece cannot have a larger momentum than the other piece, so that can't be true. B, both pieces have the same momentum vector. That can't be true either because momentum has direction and they fling off in opposite directions. So they might have the same momentum, maybe, but not the same direction, so that can't be true. C, the net momentum of both pieces is 0. That is true because the momentum of one is equal and opposite to the momentum of two, so that when you add the two together, because they're vectors, they actually just cancel out. So the net momentum of both is 0. So if you have a problem that you actually solve out, and for instance, if I ask you anything that involves the total momentum of the entire system, you can consider just adding the momentum of each of the pieces together and finding what that is. So in this case, they just cancel out perfectly. The other two statements are false for the following reasons. The larger piece moves faster? No. Having more mass doesn't make it move faster. If anything, it makes it slow down. For instance, trying to get a train up to speed as opposed to getting a car up to speed using the same force, the train is much more sluggish, so the larger piece should be moving slower. The last one says both pieces move with equal speeds. That can't be true. The larger mass and the smaller mass have different speeds based on their masses. So hopefully that gave you a little bit more insight on momentum and how it works on a conceptual level. Let me know again if you have any questions so far on any of the things I've discussed here. The last one is actually a really easy one. This will finish off the multiple choice. I just wanted to throw in a few just to kind of get you thinking conceptually, make sure you understand the concepts. So 8, a frictionless roller coaster cart runs freely through the track shown. So starts over here on the left side, moves to point A, then to B, then to C, D, and E. At which of the points would the cart have the most kinetic energy? So if you were doing a problem and I asked you to solve this problem out, you should already have an idea of which point should have the most kinetic energy, and hence what would be a reasonable answer when you calculate it. So just by looking at this picture, you can just say, oh, point D has to have the most kinetic energy. And the reason for that is if the cart runs freely along this track through all these points, so it just coasts up here. It has to slow down on its way up because it's climbing up a hill. So it's a conversion from kinetic energy to more potential energy. And when you go down the hill, it loses potential energy and exchanges it with more kinetic energy. And it does it up and down and up and down and up and down. That would then say that the lowest point in your entire problem, in this case point D, is the point with the most kinetic energy because it's used up all of its potential energy and converted it to more kinetic energy. You could also say the reverse, which is that point B has to have the most potential energy. But in this case, it would be point D rather. So point D has the most kinetic energy in this setup. So again, let me know if you have any questions conceptually on why each of the following were true. Otherwise, we will do one last problem here. This will be a comprehensive problem which combines concepts from chapters 8 and 9 together to see if you can kind of link ideas together. So on this problem right here, you have a person is driving a 2,000 kilogram car at 30 meters per second along a horizontal highway and immediately slams their brakes to avoid hitting an animal that randomly jumped out in front of them. The impulse, in the form of a friction force, was delivered over a time interval of 2 seconds, slowing the car down to a speed of 10 meters per second. Calculate the distance that the car will come to rest in. So there is a couple of things that are going on here simultaneously that we need to break up. Okay, so we're going to keep in mind that we do want to calculate the distance that the car will come to rest in at the end of the problem. So we're going to attempt to apply a principle that will allow us to get that first. And what will happen is we're going to run into an obstacle where we're missing something. And we'll go from there. So let's start by finding that distance. So to get that distance it stops in, we know that the car starts out with kinetic energy and it ends with no kinetic energy at all. Now there is one force that is responsible for slowing the car down in this problem, which is friction, so it does work on the car to slow it down. So to relate these energies together, we're going to apply the conservation of energy to this problem. So problem 9. So here's a basic picture. We're going to go from point A here. Now I'm not going to call it point B at the end where it stops, because I already know that in the problem there's more going on that's happening between those 2 points that I need to consider to solve the problem. So I'm going to call the endpoint C, and I'll talk about point B after this. Now, between these 2 points of interest, we can write that the conservation of energy states, conservation of energy, so K final, which is point C, plus U final, which is point C, equals same thing initial, all point A, plus any work non-conservative on the initial side. So I'm not going to write out and expand out every single term. I'm again going to analyze what each energy is based on and if it goes away if something is 0. So for kinetic energies are based on movement. So that means we're going to cross it out if it's not moving at any point. So at point C, we know that the car would have stopped by that point. So we can cross out the kinetic energy at C. So velocity is 0 at C, so we can cross that out. Now, that's it for the kinetic energies, because we do have kinetic energy to start with, and we're going to slow down. Now, potential energies. Again, every time we talk about potential energy, we need to consider both types: spring potential energy and gravitational potential energy. But in this problem, there is no spring ever involved in it. So that means we're only going to talk about gravitational potential energy in this problem. But even still, so if we're talking about gravitational potential energy in this problem, which is based on the height, well, the thing is that if we set the y equal to 0 along the ground, which is the lowest point that we use in the problem, well, they're both at y equal to 0. So that means that we do not use any potential energy in this problem at all, because there's no height that we're working with. Now, even if you set the y equal to 0 somewhere else so that the value is not 0 at that height for some reason, the thing is that the potential energy final and the potential energy initial are still the same value. So they still cancel out anyway if you subtract it from both sides. They still go away, no matter what. Now, what we have left is that, so we have 0 on the left side. Expand out what's left, so kinetic energy A is 1/2 mv initial squared plus our work non-conservative. So in this problem, there's only friction responsible for it slowing down. if we draw a free body diagram of this setup, which is the weight, the normal force, and the friction force in the opposite direction of motion. If we consider those forces there are two non-conservative forces because it's not dealing with gravity and not dealing with springs. So the normal force is non-conservative, but it's again perpendicular to the motion, so there's no work done by it. The friction force is along the line of motion, so it does do work, and it's non-conservative. So the work non-conservative is based on the work done by friction. And work, by definition, is the product of the force in question, which in this case is friction, times the distance that you move over, and the cosine of some angle between those two directions. So the work done by friction will be written as the friction force, which is the coefficient times the normal force, times the distance you go over. Let's call that distance d. So the distance d is the distance between point A and point C. We have a cosine of an angle that is used with the work, but the angle between the direction of the friction force, which is to the left, and the motion to the right, that angle between the two is 180. So the cosine of 180 is -1, and we usually just write it out front. So we write minus in front of the entire thing. Finally, now considering that you know that the normal force is equal to the weight in this circumstance because there are only two forces in the y direction and this force up equals the force down, there's nothing else to it, we can just plug that in as just the weight, and we can solve for the distance to stop. So in this case, if we solve for that distance, the mass will appear in every term, so it doesn't depend on the mass in this case so far. So solving for that distance, it will be, the minuses will cancel. It's v initial squared divided by 2 coefficient of friction times g. Okay. So in the attempt of finding this, we technically would only have one thing missing. It would be the coefficient of friction. Now, I don't give the coefficient of friction in the problem, but we do know something that is related to the friction force. So I would actually argue that doing this the way it is so far, going out this far might actually be a little bit too far, because now let's go hunting for the information about the friction. If we go talking about the information for the friction, we're not going to immediately get the coefficient of friction from it. We're going to actually get the friction force. So if I go back to my information over here, you'll notice that I have that the impulse in the form of a friction force, okay, so that's where we're going to involve friction, was delivered over a time interval of 2 seconds. You have an impulse, which is given not based on the other information in the problem, so you have the mass, change in velocity, so you can get the impulse, and you know the time interval. So that speaks more of the force that can be calculated. So let's actually consider that we could calculate the force from this. So what we're going to do is we're going to use the mass, the initial speed of 30. There is a speed of 10 meters per second, which it achieves before it stops. So there's a point in the middle of the two, point B, which is what I was referring to earlier. You can use that information to get the impulse, use the time, and then find the force. So let's do that real quick. So what I would then say is the friction force, let's use this, friction force, which is going to be in our net force, is the change in momentum over change in time. The impulse is the change in momentum. And we know that change in momentum can be written as mass times the change in velocity. So we expand it out like that. We plug in some values. So we have the mass is 2,000 kilograms. The change in velocity during which this force is being considered is between A and B. There is a special point right in here called point B, and we know that the speed at that point is 10 meters per second. So we're going to go from 30 to 10. So that means when we do this, final is 10 meters per second minus the initial, which is 30. So we lost 20 meters per second there, divided by the time interval of 2 seconds. And that will give us a net force of, what is that going to be? 20 divided by 2 is 10. 10 times 2,000 is 20,000. So 2 times 10 to the 4th newtons. And it technically is negative when you calculate it because it's in the opposite direction of the motion because you slow down. So this force right here is the friction force. So we can either do one of two things at this point. We can either take that friction force and we can go back a couple of steps and just write the problem with friction force in it instead. Or we can take the friction force, solve for the coefficient, and plug it back in. Now, personally, the decision I will go with here is that since I already wrote out all of this here, what I'm going to do is I'm actually going to solve for the coefficient first and plug back in since I determined that was the only thing I really needed, and that's if I was solving a problem, I'd be fixated on that goal. So I'm going to continue with that goal, and I'm going to say that the friction kinetic is equal to the coefficient times the normal force. And we know that the normal force is equal to mg. So we can solve for the coefficient, which is the friction kinetic force divided by mg. The coefficient is going to be a positive constant, so we're going to ignore everything. We're just going to plug in the magnitude of everything. So we can get that the coefficient is 2 times 10 to the 4th newtons divided by the mass of 2,000 kilograms and 9.8. Okay. So in plugging this in, 2 times 10 to the 4th divided by 2 times 10 to the 3rd should give you 10. 10 over 9.8 would give you, in this case, it's a little bit large of a value, but it's not terrible. It's 1.02 for your coefficient. You can then use that coefficient to put it back into here. So when you calculate this up here, you use the initial speed, which is 30 meters per second, square it, divided by 2 times the coefficient, which is 1.02, a little bit large realistically, but we'll use it, and then g, which is 9.8 meters per second squared. Okay. So that will give us the stopping distance because we determined the only thing that was missing in using the conservation of energy was just the coefficient friction or the friction force, which we could have found by just talking about change in momentum or impulse and relating it to force. So the stopping distance ends up being 30 squared is 900. 100 divided by, so 900, that 2 times 1.2 times 8. Okay, so the distance we get is 45 meters. Okay. So that's it. This problem is a little bit more complicated than you would probably get on the exam, most likely, just because it's a little bit lengthy. The part that you should probably take away is that you would want to use conservation of energy in this problem to solve it. So you follow the usual procedure for conservation of energy. You're missing something. So then the other thing you would then use to find the thing you're missing is combining it with momentum concepts and realizing that you have enough information to find the force using the information about its mass, its change in velocity, the time interval which that's applied over. So basically Newton's law essentially, just written in a different form, and to go find that friction force or the information related to it to then solve the original route, which is with the conservation of energy. So let me know if you have any questions on this problem in particular, and if not any questions on this problem, any general questions, and we'll wrap it up. Else, if everything is good, feel free to give me a thumbs up, and then I'll just point out a last couple of things for the next couple of days that we're going to be focusing on. Okay, looks pretty good. Okay, so then goals for the next couple of days here. So this, starting with this, wrapping this checkpoint worksheet up, so kind of skimming through this. The parts that you should ideally focus on are, I'd say, all of these individual topic questions, so 1 through 4 on this. If you can do 1 through 4 on your own completely and understand everything you're doing, then you're in relatively good shape. These alone are not going to tell you if you're ready for the exam, but they're definitely something you want to be able to do on your own, because these are definitely problems that you should be able to do on your own. So do those again on your own at some point in time, today or anytime up to the exam. The conceptual ones here are obviously not going to be part of the exam in this case, for his exam. But the things I wanted you to take away was, for instance, very simple concepts, so that when you problem solve, you should have an idea of if your answer is reasonable or if it makes sense. So you box an answer and then you need to know if it makes sense. Well, these conceptual ones are going to kind of point you in the direction of, does this make sense? So for instance, if you have a problem where you're asking for a kinetic energy of something compared to something else, you'll know roughly how many times bigger it is. Or in this case, for springs, you should know it doesn't depend on the mass here, in terms of reasonability of one answer compared to another. Anyway, that's what I would focus on, and then just the outline of this problem, not doing the whole problem. It's great if you could do it by yourself, but it's a little bit more challenging than what will probably be on the exam. So take away more concepts and applying problem-solving strategies to this. Now, as for this week, so the remaining days this week, we're going to continue covering Chapter 9. We're going to talk more about momentum. We're going to apply it to collision problems, so elastic and inelastic collisions is what we're going to focus on more tomorrow. Energies having to do with those collisions, what happens to your energy in the system. And then probably by Thursday, I'm thinking we're going to be starting Chapter 10, Rotational Kinematics. So we'll start going through the kinematics of rotation. So if you can be there in person to discuss that, it's a very important thing to start, getting a solid foundation on Chapter 10, getting those rotational kinematics down, because it gets really confusing really fast in rotation. So the next live stream is going to be Thursday night. It will cover everything from now up to Thursday on the live stream, and I'm going to soon announce the dates for the next potential live streams to study for the exam, which is next Monday. So come by in person. Otherwise, just check the announcements on my website, and I'll announce the next live stream dates regarding the test other than what we'll do this coming Thursday. So look out for that. And I'm hoping to do, we're going to do a minimum of one live stream covering one version of the practice test. But my hope would be that we can cover a couple different versions of a practice test so that you'll be prepared for Monday. And I'll get those up earlier rather than later so that you'll have time to attempt them on your own first to see where you stand before you see me do them. Because if you see me doing them first, then of course you can do it easier on your own. So give it a shot on your own first. So with that, I think everyone is good. No questions. So I'll see you in person sometime soon. Otherwise, the next live stream will be in a couple of days. So thanks for checking in, and I'll see you next time.